see a red door and I want it painted black. No colors anymore. I see a border wall and want it painted black. No colors anymore. I want it to turn black. Okay, so most of what we're going to be talking about today either comes from Purcell's E&M book, which I've already raved about before, or it comes from this more advanced book, Principles of Electrodynamics by Schwartz. This is a really nice book that derives magnetism from first principles of relativity. It's elegant and it's quite insightful. And after the stuff we talk about today, you would be able to read the first few chapters of this book and make sense of them. So if you really want to learn relativistic electromagnetism, check out Principles of Electrodynamics by Schwartz. But before we do that, I want to go over a few more questions about relativistic mass, energy, and momentum. So first question, two parts to it. We've got three different systems. Each is two particles of equal mass m and energy 3m. In the first one, both of the particles are moving in the plus x direction. In the second one, they have opposite velocities, equal and opposite. And in the third system, the velocities are at right angles with respect to each other. So figure out the ranking, which one has the largest total mass and which one has the smallest total mass. And remember, in each system, both particles have the same mass, and in each system, both particles have the same energy. And now you need to think about what is the relationship between the energy of a system, the mass of a system, and the momentum of a system. And I'll be right back. Looks like we need 2 more people to vote. Anyone else? Give you another 20 seconds. All right, let's look at the votes. Well, people were pretty evenly split. Let's look at the correct answers. System B has the largest mass. The way to think about it is that mass squared is E squared minus P squared. Now, in each case, they have the same the system has the same energy because particle 1 has energy 3m, particle 2 has energy 3m. So the energy of the system is 6m. So what it really comes down to is that you're going to have the largest mass if you have the smallest momentum, because the mass will be E squared minus P squared, all right? And in the first system, if we go back, system A, they're both going in the same direction. So if they're both going in the same direction, then that system has the largest momentum. So E squared minus a really large momentum is going to give you a small squared, or E squared minus the square of a really large momentum, excuse me, is going to give you a small mass squared. The second system, the momentum is 0, right? Because they're equal and opposite. So if they're equal and opposite, then we're going to have, then they add up to 0. Mass squared will be E squared minus 0 squared. So mass squared will just be E squared. Any questions? All right, then let's look at the next one. We've got 2 photons moving in opposite directions, and one has energy E and the other one has energy 4E. And so the system's mass is, and now you have several choices, 0, 3E, 4E, 5E. And why am I not getting to the next question? There it is. So, what is the mass of this system? All right, we still need 2 more people to vote. Still need 1 more person to vote. Okay, let's end the polling, show the results. And the opinion is very divided, but let's look at it this way. The energy is 5E because we add E and 4E. That's the energy. The momentum, well, we've got 4E going this way and E going that way. So that means that we're subtracting them because they're going in opposite directions. So the momentum is 3E. So E squared minus P squared is 5 squared minus, or 25 minus 3 squared, or 9. So 25 minus 9 is 16, which is the square of 4. Any questions? Okay, then we've got a photon hitting an electron, and it creates an electron-anti-electron pair in addition to the original electron. Now, before we go any further with the mass and energy in this case, if anybody remembers what I said last time about neutrinos, do we need any neutrinos created in this situation in order to satisfy conservation laws?
No, because they're so small.
What?
Didn't you say no because they are so small?
Yeah, we don't need to create any neutrinos because we've got an electron and an anti-electron. The only way we would need a neutrino is if we created an electron and didn't create an anti-electron, then we would need an electron anti-neutrino, or vice versa. Anyway, so everything winds up moving together. Oh wait, this is the example we did. And this is the example we did written out. I think it's too long to go through, so I'm not going to, yeah, never mind. All right, I'll just briefly go through this. So initially we've got a photon with energy E, we're still trying to figure out, and we had a particle with mass m, and the momentum of the photon was also E naught, and the momentum of the electron was 0. And then we're going to get that E naught plus m is E. And so we're going to have P squared equals E squared minus the momentum squared. And, you know, actually, I don't like their explanation. Let's just move on. Okay, finally, we've got a bunch of processes that may or may not be consistent with momentum conservation. And let's start with these three. And then we'll have to go to the next slide to finish it. First process, we got a particle moving eastward. It collides with and sticks to an identical particle at rest. And the resulting particle is at rest, but it's more massive than the sum of the original particles' masses. So originally something's moving, hits something, they both stand still. Is this consistent with conservation of forward momentum? If it is, then you would check box A. If it isn't, then just leave it alone. And instead of saying energy, I should have said forward momentum, energy, momentum. Then next one, we've got two identical particles with equal speeds, one moving east and one moving west. After the collision, the same particles move north and south with the same speeds that they had originally. So if you think that conserves forward momentum, you would check that box. Then we've got two electrons with equal speeds. They collide. After the collision, the electrons move north and south with smaller speeds than they had originally. Nothing else is emitted. So if you think that one conserves forward momentum, check that box. Does anybody need more time on this slide before I move to the next one? I will tell you right now that at least one of these does indeed conserve forward momentum. So one of the three answers so far should be checked off by everyone. I won't say which one. I thought I had modified that one, I'm sorry. Finally, a spaceship of mass 2m burns some matter antimatter fuel until the ship's mass is m. The light energy ejected from the ship has total energy m as well. So it burns half of its mass. And then finally, a particle of mass 2m decays into two identical particles, each with mass m, and they move in opposite directions at a speed of 0.5. All right, so let's start with this one. A does not conserve forward momentum because we start off with something moving, it hits something, it stops, the other thing doesn't move. So clearly the linear momentum was not conserved. In the second case, two things start off moving like this, they get close to each other, they repel and move like that with the same speeds that they had before. So before, the momentum is 0 because they're two electrons, same mass, equal and opposite velocity, so equal and opposite momenta. Afterwards, equal and opposite momenta. Furthermore, the speeds didn't change, so the kinetic energies didn't change. Whereas in the other case, case C, yeah, the momenta are conserved in this process, but because they slow down when moving north and south, that means that energy is not conserved. The kinetic energies have just decreased. Now, in this case, the light has energy m, and the ship has mass m, but the ship must also have some kinetic energy. We know that the ship must have kinetic energy because the light was emitted, so the light is moving, the light has momentum, the ship must have momentum. If the ship has momentum, it must also have kinetic energy. So this doesn't conserve energy. It looks tempting to say it conserves energy because, hey, you just got rid of half the fuel. And so if we got rid of half the fuel, then if we burned half of it, the mass must be m. And that's tempting, but remember that in relativity, mass and energy are related to each other, and mass is not a conserved quantity the way that it is in Newtonian physics. Finally, in this one, in the last one, we start off with mass 2m. They turn into two particles of mass m. Well, if we think about it, the energy before was 2m. The energy afterwards for each particle must be mass plus kinetic energy. So we're going to have 2m plus the kinetic energy. And we have to somehow set that equal to 2m, which is what we initially had. That only works if the final kinetic energy is 0. Any questions? Okay, then let's go to electromagnetism. All right, so we're going to answer the famous question posed by Insane Clown Posse. Bleeping magnets, how do they work? So let's consider a perfectly mundane wire, and it's got a current running through it. And there's no net charge on the wire. Well, even though there's no net charge, there are charges, of course. There are the positively charged nuclei, or strictly, really the nuclei are standing still, and also the inner shell electrons, although they're moving, they're not going anywhere. They're just orbiting the nuclei. It's only the outer shell electrons that are able to travel in a current. So we've got a wire. We've got a density of positive charges. We'll call that lambda naught. We've got an equal and opposite density of negative charges. We'll call that minus lambda naught. And this is charge per length. and we have a test charge sitting down here. Now, if the test charge isn't moving, well, we got a stationary charge in an electric field, and in a magnetic field, and magnetic force is QV cross B, but V is 0, so no motion, nothing really to say. And furthermore, we could add that there's no electric force because this is neutral. If this is neutral, then there's no electric field. So there wouldn't be a whole lot to say. What if this charge is moving? All right. And I just realized that I put the wrong subscript on the V. My apologies. The wrong subscript on the V. We'll deal with that later. Anyway, what if this test charge is moving? If the test charge was moving like this, well, now let's think about it. We've got a wire. We've got the electrons going to the right, which means that the current is going to the left. So the magnetic field, I take my right hand, I curl it around, I curl it with my thumb pointing in the direction of current, and my fingers wind up coming out of the page if, that everything got mirrored around with the camera on Zoom. But if you just put your hand in front of the computer screen and point your thumb along the direction of the wire, when you curl your right hand, your fingers are going to have to come out of the screen. So you got a magnetic field coming out of the screen over here, all right? And when we cross V with that, we have V pointing in the direction of the, pointing to the right. So we put our fingers to the right, and then we curl our fingers in the direction of, why is this not working? Fingers to the right, curl them into the direction out of the screen, and everything's mirrored with the camera. So I curl my finger, start with my fingers to the right, curl them out of the screen, my thumb points down. So this test charge is repelled downward. And we want to figure out why that is. And you can say, well, we already know why that is. We took physics 1520, there's a magnetic field. Sure. But we're going to jump to the rest frame of this charge, to the frame where this charge is not moving. Because in the frame where this charge is not moving, it can't feel a magnetic force. There might be a magnetic field in that frame, but in its reference frame, it can't feel a magnetic force. So there's got to be some other force acting on it. But before we do that jump to another reference frame, we have to first calculate the force so that we don't just have a predicted direction for the force, but we have a predicted magnitude that we can compare with when we get a calculation in the reference frame of the test charge. So we'll calculate the B field. We use Amperes Law. If we were to draw a loop around the wire, then we would curl the magnetic field around that loop. We would take the integral along that loop, and we'd have B times 2 pi r equals the charge passing through it, which is going to be, it's going to be mu naught times the current, and the current is the number of charges per length times the distance traveled per second, so lambda VE. And so we get this expression for the magnetic field, and then when we take V cross B, there should be a sine theta, except that the B field is out of the page and V is to the right, so theta is 90 degrees, sine theta is 1, and this is what we get. Any questions on that? All right, well, if we jump to the reference frame of the test charge, in its frame it's standing still. As far as it's concerned, it sees the positive charges start to speed up and move to the left. And when things speed up and move relative to you, they seem to shrink. So it thinks that the positive charges have gone closer together. So there's a high density of positive charges. On the other hand, it's moving in the same direction as the electrons. Maybe not at the same speed, but still, in that reference frame, the electrons are moving slower than they were in the laboratory reference frame. So the electrons have slowed down. And when things slow down, they get bigger. The spacing between the electrons gets bigger. So now, with the larger spacing, there are fewer electrons per unit length. We have a lower density of negative charges. And the effect of all this is that the wire now has a net positive charge, right? High density of positive charges because they've all shrunk and gone close to each other. Low density of negative charges. And so our positive test charge is repelled from the wire, just like we calculated on the previous page. Any questions? Anyone? Okay, so that's the qualitative idea. That's the basic idea for why it is that we must be seeing a repulsive force between that test charge and the wire. But we can go beyond just saying, hey, we get the same qualitative prediction from relativity. We can get quantitative. We can calculate the velocity of the electrons in the reference frame of our test charge. We use the velocity transformation that we derived a couple weeks ago. We can calculate the velocity of the nuclei. It's just the relative velocity of the test charge in the nuclei. And so we can compute the density of the nuclei. The spacing between them shrunk by a factor of square root 1 minus v squared. So the density must have increased by 1 over that, because if it's charge per length, well, it's going to be the length or the spacing between them that goes in the denominator here. Any questions on that idea? All right, spacing between the electrons is more complicated. And in their own frame, they must be pretty far apart. So if they're pretty far apart, their separation is large, their density is low. So in their own frame, not in the lab frame they're moving. In their own frame, this is their density. In the frame of the test charge, their density must be whatever would be in their own frame divided by this factor, where this is VE prime. This is the speed of the electrons relative to the test charge, because it's the test charge that's observing. So we're going from the density in their own frame to the density in the frame of someone who sees the electrons moving at VE prime. So first we take minus lambda naught, the density in the lab frame. We multiply by square root of 1 minus VE squared, and we divide by the square root of 1 minus VE prime squared. And then we can plug in VE prime. And then to get something quantitative, we need to do a whole bunch of algebra, which is usually just asserted in all of the books. But basically what you would do is you've got this messy expression in the denominator, and that expression, one of the terms has its own denominator. So we take the thing that would be in the denominator of one of the terms, and we write the 1 as this messy thing over itself. So now we've got a common denominator between the two terms that we're subtracting. And then we've got 1 over the square root of this mess. And 1 over something is that something. So we bring the square root of this mess up top. And that mess is a square, and the square root of a square is the original thing. So we get the 1 minus VEV there. Then down on the bottom, we've got a whole bunch of mess. And we get a few things that cancel. And after we cancel those things, we find that the denominator can be written as the square root of this product. And one of the factors in this product shows up top. So we can cancel something. And so we eventually get this. We get that this is the density of the electrons in the frame of the test charge. And then we add to that the density of the positive charges, because we want to calculate the total charge density. And we get some cancellation, and we're left with this. Now, we've got a line charge, all right? There's a net charge in the frame of our test charge. This wire is charged. It also has a current, but the test charge doesn't see any magnetic forces because in that reference frame, its velocity is 0. So we get this for the electric field, because the electric field is linear charge density over 2 pi epsilon naught r. And of course, that density has a VEV. Now, here's the thing. If we look at this formula, we've got VEV over square root of 1 minus V squared. Some of this looks familiar, like the lambda naught VEV over 2 pi r. If we go back a few pages and look at the force we had before, lambda naught VEV over 2 pi r. There's also some differences. We've got an epsilon naught in the denominator. And here we've got this factor. But a few pages ago, when calculating magnetic force, we had a mu naught up top instead of an epsilon naught in the denominator. The thing to remember is in relativity, we're almost always talking about V over C. Anywhere that you see V in relativity is probably V over C in regular units. So this VEV should be VEV over C squared. So we should have a C squared down here. So we have an epsilon naught C squared in the denominator. And if you think way back to early in the semester, we calculated the speed of light from Maxwell's equations. And we got 1 over epsilon naught C squared equals mu naught. So lo and behold, we've got a mu naught up top. And we've got that the force in this reference frame, well, we've got the Q, we've got the lambda naught, we've got the VEV, we've got the mu naught, and we've got 2 pi r. Only thing that's missing is this, and we'll get to that. But before we get to that, are there any questions on the process that we followed? Again, the thing to take away is that we just calculated an electric force using the charge density in that reference frame. Then we went to almost grown-up units. We went from grown-up units to more traditional units. In truly grown-up units, we don't have mu naught and epsilon naught are 1, just like C is 1. Some people say that epsilon naught should be 1 over 4 pi. Those people are crazy. Heaviside Lorentz units rule. All right, so we got the same force as before, except for this factor. Now, Fy prime is dPy prime over dt prime, because force is derivative of momentum. You might be saying, well, isn't F equal to ma? Sure, but a is the derivative of velocity. So ma is mass times derivative of velocity. Mass is a constant, so we could say it's derivative of mass times velocity or derivative of momentum. So dPy prime equals dPy. And dt prime is, I don't know why I put VE there. I'm sorry about that. I will fix that. dt prime is square root of 1 minus V squared dt. So when we put all of this together, we get that the force in another reference frame is essentially equal to the force in the lab frame, with this additional factor to account for the fact that time is different in different reference frames. Any questions? No questions? I just told you the electric and magnetic fields are the same thing, even though you had learned in 1520 that electric fields show up in like chapter 20 of the book, and magnetic fields show up in like chapter 27, so they must be different things. Or maybe it's not 27, but you know what I mean, somewhere around there. All right, well, where do we go from here? Think about the fact that for the first part of our relativity coverage, we just kind of did different cases. Like, oh, here's how we calculate the coordinate time and see how coordinate time changes. Here's how we calculate space-time interval. Here's how we calculate proper time. Then we came up with the Lorentz transformations, a more systematic set of transformations to take us from one frame to another. There is a systematic structure to electromagnetism, but we have to kind of switch our formalism up a little bit. Force is derivative of momentum with respect to time, and the numerator is part of a 4 vector, and the denominator is not invariant. So what we've got is we've got a 4 vector, or a part of a 4 vector, over something that isn't invariant. So we wouldn't expect E and B to be invariant between frames. We wouldn't even expect them to transform via Lorentz transformations. So this E and B, however they transform, is going to be messy. It's not going to be as elegant as Lorentz transformations. But there is something that transforms as elegantly as Lorentz transformations. There's something called a vector potential. And without even talking about relativity, we could just think about, well, we know that the electric field, at least in the static case, is minus the gradient of potential. Now, before we knew relativity, people figured out that sometimes it might be easier to write the B field as the curl of another vector, called the vector potential. Now, if that's all that we did, if we didn't have them coupled together, well, it would be kind of boring. But the vector potential is connected to E. And we know that because we know that the curl of E is minus the time derivative of B. And this is often non-zero, time derivative of B. So if the time derivative of B is non-zero, then the curl of E must be non-zero in many cases, which means that E needs to be more than just minus the gradient of V. What I wrote here is perfectly valid as long as charges aren't moving. But as my E&M professor said when asked what happens if charges are moving, he said all hell breaks loose. So let's break all hell loose. All right, so E must be minus the gradient of potential plus something else. And the curl of E would be the curl of that something else. It would also be minus the derivative of B. And minus the derivative of B is minus the derivative of the curl of A. And we can take derivatives with respect to independent variables in any order we want. So that something else must be minus the derivative of A. So E is this, minus the gradient of V, minus the time derivative of A, and B is curl of A. And furthermore, we know that the Laplacian of V is minus rho over epsilon naught. So electrostatic potential is produced by charge distribution. Now you can ask, what produces A? Let's look at our 4 Maxwell equations. The first one, well, we're doing them in different order than usual. Del dot B is 0. That's guaranteed if B is the curl of A, because the divergence of a curl is 0. And this equation, we just talked about how this one is guaranteed to be satisfied if E is written that way. Let's look at the divergence of E. We've got del dot E is minus del dot gradient of V minus the gradient of the time derivative of A, or minus the time derivative, did I say gradient? Minus the divergence, sorry. Minus the time derivative of the divergence of A. Let's just hang on to this for a little while. Meanwhile, the curl of B is the curl of A, and we worked out an identity several weeks ago for this. Get this nice big mess here. We've got the Laplacian of A and something uglier. But notice how we've got the divergence of A here and the divergence of A there. We're going to do some work and we're going to get them to cancel. We get mu naught J here. So hey, Laplacian of the vector potential is the current density. Laplacian of the static potential is the charge density. That sort of makes sense, except we've got all these other terms lurking around that we have to do something with. We've got the time derivative of the E field, which is all this mess. All right. So what are we going to do? Well, we've got in the time derivative of the E field, we've got the time derivative of the time derivative of the vector potential, which means we've got the second derivative of vector potential with respect to time somewhere in this equation. We can rearrange things and we get this nice thing here. We get 1 over c squared, second derivative of A with respect to time, minus the Laplacian of A equals mu naught J. We've got a wave equation set equal to a source. That's elegant. It's just that we've got this extra mess here. We've got a mess that involves the divergence of A and the time derivative of V. And believe it or not, we can set them equal to 0. And setting them equal to 0 actually turns out to be a really important thing that gets revisited again and again in more advanced realms of physics. You see it in more advanced E&M. You see it when you do the quantum theory of light. You can't do the quantum mechanics of light and photons without delving into that at least a little bit. It shows up in particle physics. It keeps showing up again and again in the higher realms of physics. But the basic idea is related to something simple that you already learned. Adding a constant to the scalar, to the electrostatic potential changes nothing. All right, if I announce that I'm going to increase all of my voltages at every point in space, well, the electric field is the derivative of voltage, or at least the static electric field is the derivative of voltage. So if I add a constant to something, I don't change its derivative one bit. Now, we take some pretty complicated vector derivatives when we write down E and B. And it turns out that we can add not just constants, but add functions that change. We can add special types of functions to A and V in such a way that these complicated combinations of derivatives don't change. We're going to add the gradient of something that's often called phi or lambda. It gets a number of names, but it's called the gauge function. I'm calling the gauge function phi right now. There's a number of things we can call it. We could add the gradient of some function to A. It's not going to change B because B is the curl of A. And the curl of a gradient, as you learned in Calc 3 and as we reviewed a couple months ago, the curl of a gradient is 0. So if we add the gradient of a function to A, we don't change B one bit. All right, now it could change E unless we also change the voltage as well. So if we change the voltage, if we say, all right, fine, I'm going to add gradient of phi to B, and I'm going to subtract the time derivative of phi from V. Then, well, let's see, when we take the gradient of, or minus the gradient of V, we get plus the gradient of the time derivative of the gauge function. And then we subtract off the time derivative of A, which means we subtract off the time derivative of the gradient of the gauge function. And these two things cancel. And at this point, you're probably thinking to yourself, okay, we can add this function, but it changes nothing. What is it? What is the physical meaning of it? That I don't have a good answer for. I mean, what is the physical meaning of adding 17 volts to the potential everywhere in space? There is no physical meaning to it. It changes nothing. The best I could say is that sometimes adding or subtracting some constant from the voltage everywhere makes it easier to calibrate your readings. You decide, okay, well, if I add or subtract this constant, then I'm going to get the voltage equal to 0 at some place that's very convenient to work with. Here, by adding or subtracting the gradient of a gauge function to the vector potential and the time derivative of the gauge function to our static potential, I've made some equations convenient. If adding or subtracting voltages is convenient for experimentalists because we can decide where we want to calibrate our voltmeter to read 0, adding or subtracting derivatives of gauge functions is convenient for theorists because it makes certain differential equations much cleaner. All right, so if we plug all of that in, remember before, we had this messy equation for A. We had something very elegant, the wave equation, something very elegant, current density acting as a source, and something ugly, the gradient of this combination of terms involving divergence of A and time derivative of V. Well, if I make my gauge transformation, I get a whole bunch of messy terms in here. This doesn't look any cleaner than it did before, except that I get to pick whatever I want for my gauge function as long as the gauge function has well-defined second derivatives. That's pretty much the only thing. As long as I can take the second derivative of my gauge function, I can make it anything I want. So I'm going to say that my gauge function satisfies a wave equation, and all of this stuff here, this divergence of A and this time derivative of V, the stuff that I didn't want in my equation for the vector potential, that stuff is the source term for my gauge. I'm basically saying that my gauge function is created by all the stuff that I don't want, and that's how I'm getting rid of it. So if I can construct a gauge function satisfying this, then I can modify A and V. And when I modify A and V, I get a very elegant wave equation with a source term. So my vector potential is created by current densities. And here's a nice side effect. If I take the divergence of E, well, the divergence of E is going to be minus del squared V minus the time derivative of this divergence. But we already set things up so that this divergence of A was the time derivative of V. So I got the time derivative of a time derivative. And what I finally get is that the static potential, it's no longer static. The electric potential, let's just call it that and leave it at that. The electric potential, which we normally talked about in electrostatics, obeys a wave equation, and the source term is charge density. Any questions? All right, now I'm going to prove that these source terms, the things that create the electric potential and the vector potential, that rho and J transform like 4 vectors, that they obey Lorentz transformations. So let's say rho naught is the charge density in some frame where the charge is stationary. Then in another frame, rho must be rho naught over this because all the charges got closer together. And if this is charge over spacing between charges, well, that spacing got smaller, so we have to put this smaller thing in the denominator. And the current density, we talked a couple months ago about the fact that the density of any flowing substance that could pass through a surface, the current density of that stuff, the flux, is the volume density, the amount of stuff per unit volume multiplied by the velocity. So J is rho naught V over square root of 1 minus V squared. So we've got constant over square root of 1 minus V squared and a constant times velocity over square root of 1 minus V squared. This should look a lot like the energy momentum 4 vector. Different constant, but same structure. The energy momentum 4 vector is mass over square root of 1 minus V squared and mass times velocity over square root of 1 minus V squared. So all we've done is change the constant, but if this transforms like a 4 vector, then so does rho J. So we've got the wave equation operator acting on either V or A, giving you either minus rho or minus J in units where mu naught, epsilon naught, and C are 1. And this wave equation operator is the same in all frames, which you're going to prove on the homework for Friday. So we've got something that's the same in all frames, acting on this and giving a 4 vector, which means that V and A must be 4 vectors. And so V and A transform like 4 vectors. V and A satisfy, or V and A can be transformed via Lorentz transformations. So even though electric and magnetic fields are complicated, the potentials that they derive from obey Lorentz transformations, which makes it much easier to calculate electric fields in different reference frames. Because what you do is you calculate V and A in one reference frame, you use those combined with the Lorentz transformation to figure out what they must be in some other reference frame. And then you take derivatives of those things and you've got your electric and magnetic fields. Any questions? Electromagnetism has a relativistic structure underlying it. This is why Einstein titled his first paper on relativity on the electrodynamics of moving bodies. And this is why the structure of Maxwell's equations was the hint that we need the theory of relativity. Somebody must have a question on this. Statistically speaking, most people believe that they're going to grad school for theoretical physics. Once they get to grad school, most people wind up doing experimental physics for a bunch of reasons. Partly that theory is not as much fun as they thought, and partly that there's money in experiment. But most people believe they're going to grad school for theoretical physics. So somebody must have a question on this stuff. Or have you all already figured out that you're going to be experimentalists? Somebody must be curious about this. Nobody's curious? You're making me sad. Somebody must be curious about this. All right, fine, don't be curious. On Friday, we are going to talk about relativity, gravity, acceleration, and GPS. And also on Friday, I will announce when the final exam final exam review session will be. The final exam from last semester has been posted under course documents, same place I posted last semester's midterms. So you should be working on that. You should be working on old problem sets. And as always, I'm available for questions. If it's not during my office hours, you can if it's during my office hours, just email me and I'll be checking email during office hours, and then we'll set up a Zoom right away. Have a good day.